Hello. Um, yeah, let's get started. Today we are doing problem 7. I'm recording this last because I found solutions to this problem. However, it was the solutions were very I mean, the solutions I was initially thinking, well, why don't we just do number 6 and then merge it? But because I spent 30 minutes explaining 6, which I think I did very well, and I try really hard to explain how exactly 6 would work. If I did it that way, it would be too similar to 6, and then for 7, I'm just going to be re-explaining 6 with a couple of differences in terms of merging the after I've already merged and stuff. So it's a very similar problem. So I decided that I didn't like that. Um, I I decided to look into other solutions, which were a lot harder. I know that I didn't think the solution that everyone used was any better. I mean, not by much. Um, but because I already did 6, so number 7, like what everybody has is they essentially did number 6, and then they in the end merge all the uh nodes together. So because it was already sorted. So they merged these two and then merged this with this and then merged that with this. So yeah, as you can see, I already started scribbling all over the place last night because otherwise it's going to take me like, I don't know, 40 minutes to say everything and draw everything. So I have the pseudocode here. I have the just I used it to kind of iterate through it and step through everything to make sure I have it. I may not remember everything from last night, but yeah. So let's just go through it. So it's the 7 is asking, given a linked list where every node represents a linked list and contains 2 pointers of its type, a next pointer to the next node, a bottom pointer to the linked list where this node is head. You have to flatten the linked list to a single linked list, which is the example given in input that I drew out. So at first when I read the question, I was like, what? What's going on? And then I looked at the input and I said, well, they look like lists that should be, um, merged because I don't know how else you would do it. And then it was very similar to 6, so I decided to try something else just for the heck of it. So what essentially this question wants is these are all linked lists here. So that we know of. So there's a linked list here, there's a linked list here, there's a linked list here, there's a linked list there, there's a linked list here. Do you know what I mean? So we have to get all of these linked lists sorted. It's already pre-sorted, but we have to sort it when we merge it, sorted, and return it in one single linked list. So it has to be sorted. So it would go, we have to scan all of these for the min, which is like 5, which is where we're starting. And then we have to go, okay, like what's the next largest to 5, but still what's the new min? So that's 7, and then so we change our pointer from well, I won't change the pointer, but we go, okay, the pointer that's going the curve dot next's pointer is now 7, and then 7 the next min is 8, so 7 will go point to 8, and then 8 will point to 10, and then 10 will point to 19. I mean, I already drew the lines here. I don't know why, but I did it like this. I'm sorry it's in yellow. I did this last night and I did not mean to keep it. It was just notes for me. But since it's here, I might as well. Because this new setup makes me able to do this. So I could just scroll down and write everything in black and stuff. So these are just notes. I'm so sorry about the yellow. These are notes for me. It takes a long time to explain the process. So yeah. But yeah, so the output, the, yeah, the output should have one singly linked list that's small to large. After we're done with everything, which means that we're gonna have to change a lot of pointers. So it's not an easy problem. This was the hardest in the list for me because 6 was sort of kind of hard, and then 7 was like harder, and I wanted to do 7 differently. So yes, I am using min heap. Don't bother reading this; it's too light. But yes, it's just notes for me. We are using min heap, and we're going to pop out. We're going to start at 5, and then we're gonna assign it the head and cur at 5, and then we're gonna check 7. Oops, and we're gonna check the pointers that's 45 is pointing to, which is happens to be 7 and 10. And now we're going to put 7 and 10 into the min heap, and then the min heap is going to do what it does, and it's going to say 7 is the smallest, so we pop out 7, and then we direct cur dot next, or basically 5 dot next is next arrow to 7 instead of 10, and we're not afraid of losing 10 because 10 is still in the heap. So then we uh, moved. We go find what 7 is connected to, because we are now at 7. Wait, yeah. And then we have to check. Oh yeah, no, sorry, my bad. I got ahead of myself. I forgot step number 4. So after we move cur's next pointer to 7, then we have to. We don't have to worry about 10, but we do have to point 5's bottom pointer to now null. Um, and we have to add um 7 pointers next pointer to the heap as well, and the bottom if it has a bottom, which means 8 and then 10 goes into the heap, and then we have to increment the cur to cur.next will become 7. So yeah, and then this while loop, this part is the while loop. This part is the while loop, and then once the while loop finishes, we would have gone through the entire list, and then we just return head, which will have the pointers going the cur. Oh no, the head. That we changed cur, but we never change head. We return head, which will have the pointers going in a singly linked list, to hitting all the nodes that we want. That's been sorted by the heap and returned. And yeah, that's kind of how we're going to approach it. I think the code will probably make more sense than me just saying it. But yeah, it's all the arrows here. I was just like doing the while loop out one by one because I'm like, needs all the steps. So basically, every single time we hit a node, so 5, 7, 8, or 30, or 10, or something like that. Every time I hit a node, we go, okay, is there anything on the left of it? I mean, on the next of it, or on the bottom of it? And if so, put it in the heap. So, and then we save it in the heap, and we don't have to worry about losing nothing. And then like, yeah, and then we just sort using the heap to pop off, and then we go to that, and then we move cur um, to the whatever we just popped off that we sorted and we process and stuff. Yeah, it's complicated at first, but to me is easier, I think. Especially because heap is doing kind of the hard work of just sorting, and all we have to do, and they're like saving things, so I don't have to like save random stuff and worry about losing pointers, and I mean losing nodes from switching pointers and stuff. So yeah, I think it's quite beautiful in this method. I didn't think of it. I needed to ask. I needed to ask the help of my friend. He's an engineer, so but yeah, and there was a lot. I learned a lot. I think I learned more from that experience with him than reading Geek for Geeks. But I wanted to do it a different way. So I was like, you know what? I'm gonna consult. I'm gonna bother him. I'm gonna consult him on this. Because all the solutions I saw were just merging the different merges. Like, no. um. So yeah, the runtime time complexity, because it's heap and it's like sorting and stuff. It's n log n. I was confused initially because I thought n log n was binary search. No, I got it and I basically reversed it. So in my head, I leave myself these notes and I end up, I don't know, a few months later, I come back to it and it's actually the opposite of what I remember. So I thought it was called where I thought we were gonna use a max heap because if you need to find a if you get a max heap, then you find the min. No. The min heap finds the min. But in my head, I was like, oh, it's the opposite. And I don't know. I was like, we use a max heap, right. No, we don't use a max heap. And then I thought n log n was for binary and log n was for like sorting. So heap is a sorting thing, so it's n log n. So I got that in reverse. Basically, I should not trust my own brain, is what this whole thing tells me. It's quite embarrassing. But yeah, this is n log n because we have n list of nodes that we have to sort, and the space complexity is linear because we have to make a heap, and that's space, right? I'm not sure, but I'm pretty sure because it usually is. And then we're just adjusting pointers, so we're not making additional space in terms of that. But it really depends on the size of the heap and the nodes and the input and stuff. I don't know. Yeah. So yeah, time complexity is n log n and space is linear. Okay, let's get into the code. Okay, so I'm just going to, oops. I feel like I should do it a different color, but I don't actually. How do I erase this? Okay, there. It was bothering me. It was just ugly. Yeah, so this is the notes I have and then the code. I wish I could do it. Hold on. Okay, I know what to do. The beauty of being able to do this is just awesome. Look, look what I just did. I'm just gonna move it. See, I said don't worry about it. I'm just gonna move it and I'm gonna put the code here. Yes, I'm very happy about this. Also, I could probably just erase the arrows because it'll let me. Because it lets me do this now. Look how cool that is. So cool. Look at that. Very cool because it was so messy before. Like, this is so helpful. Why isn't everybody not using like Google Keep? Why does anybody use any other whiteboard? Just use Google Keep. It's awesome. Just like I wish I could do more of these videos because I get to play with this and it's so fun and so much better than the other whiteboard. Okay. So yeah. I don't know what also I forgot to say I asked about a dummy node. I think a dummy node would help because but I thought it was tricky. I thought it helped. So we don't have to worry about naming stuff because naming got really confusing between cur and next and stuff like that. So with a dummy head, I think we could just throw the 5 into the because the 5 doesn't actually go in the heap. We could just throw the 5 into the heap, and then the heap would just throw it back and be like, "Yep, connected," you know. So, but yeah, no dummy head for me. It's only because I already absorbed the traditional way of doing it without dummy head, and yeah, I don't know. I don't feel comfortable explaining dummy head. But I thought about using it. So let's see. So we are going to use the node, and the node has a value, a next, and a bottom. Each node has a value, a next, and a bottom pointer. And then we are going to, I don't think I've defined the node class. So I'm just going to go, well, we have a push, we have a pop function. So we're going to, let's just say we have the node, we have the push function, we have the pop function. Now we're going to just define flatten link list, I guess. Flatten LL. Okay. And the input of head, which is where we're starting. Okay, so now we're gonna create currently an empty heap. Oi. If head dot next, so this is head. Head dot next is not none. Then we are going to push that node into the heap. Yeah. Since well, maybe I should have written the push node function, but it's just push node. So we're going to pretend like this is, I wrote the push function. Heap head dot next. So this is saying we're going to push the head dot next into the heap. I could have said this just like heap dot push and then parentheses head dot next, but yeah. But if head bottom pointer, I think it's called bottom pointer, then we're going to push that in as well. So we're pushing both on the bottom. So we're pushing every time, like I said, every time we go to a node, we are pushing in whatever the heck it's pointing at directly, whatever the next is pointing at directly, and pushing it into the heap. Because we know we're gonna have to sort it, and get to it eventually. So we are processing it. I think it's called. We're just every time. Yes, that's a good word. Every time we go to a node, we're processing it. And now this is where the while loop starts. This is just saying what's gonna happen. So cur now is head. Now we have assigned cur to the head, and head to cur, sorry. And so as long as there's what's it called, items in the heap, this while loop will be valid. I'm gonna run out of space, so I'm gonna shrink. Oh, it's beautiful. Look at that. I'm gonna run out of space, so I'm just gonna do this. Move everything out of the way. Oh my goodness, this is so great. This is so nice. Look at that. Look at that. That's so nice. I'm so sorry about the yellow. Really can't see that. Oh my god. But yeah. Let's see. Now it's even smaller than yellow. So while there's still stuff in the heap, so while the length of the heap is larger than 0, we are going to just pop off the heap, the min in the heap, and assign it. And this is where it was confusing. We're going to assign it to this thing called next. So we're going to pop out the node, a heap, and assign it to next. And then we're going to assign cur dot next goes next. So we're making sure that we're moving the pointer, and then we're going to take away the current dot bottom, and then we're going to switch it. Like we are basically on step, what's it called, 4. Yeah, so we're on step 4. Oh, I could write the steps. So this is step 3, this is step 4, this is step 2, and this is the step 1 is here. So yeah. And man, the writing is terrible. Sorry. If next dot next, now we're gonna go. Okay, if the next of next is not null, which basically checks like whatever. So like if we're on 7, then we're gonna go, okay, is there anything after 7? Which there is. There's a pointer pointing to 8. So, oh wait, is not none. Sorry. I'm doing multiple things at once here. Is not none. Then we're going to just repopulate or populate more the heap. So we're going to push a node into the heap, and where it's the node that we're going to push is next dot next. And we're going to do the same thing but bottom, because we're just processing every node that has pointers when we arrive at it, if we arrive at it, so that we can save everything. And oh, I forgot the if statement. Okay, whatever. Yes, I think the code is more friendly. This code is more friendly than doing it merging the merging way. So next dot bottom is not none, and then now we are currently now at step 5. Now we're at step 6, which is just simply 6 is oh gosh, I gotta move this too. Okay, now we're at step 6, which is basically in moving. Where's my mouse? Where did it go? Oh, there it is. Moving. We're gonna increment and move cur to next. So we are now having cur instead of at 5, it's at 7. So that we could return to the start of the while loop if need. And yeah, and go do everything again and process every node until there's no more. And that's what's gonna happen. And then we return after it's all said and done. Then we return head, because head is not something we have changed. So it's just getting all the pointers, and we just return head. Yeah. So that's it, and that's the code. I feel like it's quite messy, but it's readable, sort of. Oh well, it's too big to be shrunken. I can't. Can I zoom out on this a little bit? No, I can't. Okay, that's okay. Yeah, and I already discussed time complexity and space. But yeah, it's n log n and on n t and s, and that's it. Yeah. Okay. Well, that was the last problem, and I'm done. I learned a lot. It was also hard, and it makes me a little shy. Did I forget anything? No. Okay, that's it. Oh my god, the last video. I'm done. I'm gonna graduate. Bye bye.